Bismillahir Rahmanir Rahim. So today we are going to have this webinar on this topic: electrical
Okay,
signature of
on
power
demand, on
equipment
demand,
failure
on demand.
on demand under the umbrella of United Engineering Services. We, as a consulting firm in electrical sector, situated at Defense Housing Society, Defense Housing Authority, Karachi, and we used to conduct monthly webinars on different electrical related topics. So today we are having this webinar on a very important topic, which is not so much new, but it's really, you can say, people are speaking about that. That is electric signatures of power equipment failure. Basically, when power equipment failure occurs, there are some, you can say, sign or any indication, health monitoring. Either that can be examined using the voltage waveform or current waveform. So they both can be the source of evolution for evaluating the different failures occurred in that equipment. Starting with that now, let me introduce myself first. I am Engineer Saifullah Baloch. I have just recently completed my Bachelor's of Engineering in Electrical Power from Mehran University of Engineering and Technology, Jamshoro, and I'm working as an assistant engineer at United Engineering Services. Now, as you know, that many power equipment failures, and cable as one of them, capacitor switch or power line and electric motor. These are all are equipments. There are all electrical equipments. So whenever any failure occur in these, there something we can observe that can be some, you can say, a spike or any dip or any strike, any transient variation of voltage or current in that waveform. This equipment health monitoring using the current or voltage waveform gives you the idea that what kind of fault that has occurred. And in the past years, the scientists, the researchers, and engineers are working that how we can judge the health and predict the remaining life of that equipment using the condition health monitoring. And with that, power quality is also examined using such waveforms, that these power quality disturbances which disturb the flow of electrical power towards the electrical equipment from the supply gives you an idea that to how much extent that equipment can tolerate such failures and such disturbances. Now, how to analyze such waveform type power disturbance and how to extract information from these waveforms, we'll be going into the depth of equipment condition monitoring. That is also an essential part of these signatures. Power quality disturbance are those electrical disturbances that can lead to power quality problems. That's truly, you can easily understand this sentence. Equipment failure may or may not result in disturbance of concern from power quality perspective. That's also clear. Now, as we have took this material, data, definition, and all this information from an technical report that is already present at the Power and Energy IEEE Power and Energy Society Resource Center. You can just Google it, and if you're an IEEE member or PACE member, you can easily download that technical report and get a great amount of knowledge regarding such signatures. Now, according to the IEEE standard 1159 2009, Power quality disturbance are classified as shown in the table which we have just on the next slide. Now you can see over here that there are some different categories for different disturbances in power system, like transient, short duration, short duration variations, long duration variations, power fluctuation, power frequency variation, voltage imbalances, waveform distortions. These are the different kind of disturbances which an power system can experience while different operations. Now, as we know, the transient occurs due to different causes. There may be a lightning strike or any short circuit which which can occur in the power system and causes a transient behavior of power, and that can be impulsive or oscillatory. These both are the part of transient disturbance. And this is the typical spectral content, that how much of time it will how much of frequency or time period that these can have, typical duration, how much time that can be you can say seen on that waveform, and its typical magnitude, how much of their amount that generally we used to give in per unit, because this is very common, and we can this help us out in solving the complex engineering problems, so we take here as a per unit value. Short duration variation, there can be interruptions, swags, swells, and the duration are here, and the magnitude is also present in this table. Long duration, sustained interruptions, under voltage, over voltage fluctuations. So these are all data which we have extracted from the IEEE 1159 standard. Now, let me just give you an overview, an introductory and elementary view of sample of signatures, that can be seen if you are evaluating, if you are taking the readings for the any power quality disturbances. Now, as shown in the figure, there are two pictures you can see. One of them is showing the upper one, A, that is impulse transient, and the second one is oscillatory transient. Impulse transient, as you can see here, there is an change in voltage. Okay, so this the voltage which has just crossed the zero line over here has moved a little part in the negative side, and again it does not continue from that same negative one, but has started from this, and certain level of voltage uh, towards the next cycle, and then it went into negative one. This is an impulse transient, a very short transient for a very short time. Now for the oscillatory one, oscillatory means, by word it is clear that oscillation means multiple times, again and again. This is something oscillatory, and it continuously moving on the upper peak of this voltage level. Now here you can see this transient has a many short waveforms, you can say a periodic changes in the voltage, and at some part of it, it has rise to a very high amplitude, that is more than 200 of volts here. So this is an oscillatory transient. Now let us move on the next slide. This is an sag, the voltage dip. You can see on this waveform, and swell also here. Okay. Now let me just I'm just giving a brief introduction of that, because many of you may have this you can say elementary knowledge, but as I find it suitable that to explain the elementary aspects of this topic, so that it can help you out to understand the different you can say phenomena which we will discuss in the further slides. Now, this is a signature of DC component. This one, Here you can just see it and memorize it, and if you will find any other waveform while you are working in a field in academics, you can just match it out and you can easily evaluate that this is a signature of DC component. This is an of subharmonic component. This is of harmonic components. As you can see, there are multiples of frequencies on the upper and lower side of the waveform, crest and trough, and signature of an intraharmonic. This was harmonic, subharmonic, and this is the intraharmonic. The multiple frequencies of multiple voltages there are felt on the single waveform. Here you can see this, and these are the signature of voltage distortion. Okay. Now, we have just already covered this, but you can after this table. Okay. Now, these are the disturbance groups. Transient, intermittent, that is same as the previous one table, but it has another parameter, that is severity parameter, that how much of this you can say what parameter of that disturbance actually make it severe for the power system, how it will make the system more damaged, or from which part of that kind of disturbance has the power system more strange or more unwanted, undesirable effect on the power system. First is magnitude, as in the transient disturbance. The transient disturbance causes the severity by its magnitude and duration. Intermittent causes the intermittent uses its magnitude and frequency, and steady state disturbance and you can say uses its magnitude to disturb the system. Okay. Now these are the parameters of that kind of disturbances that causes the severity in the system. Now, it is very important to note that power quality is primarily concerned with the quality of supply voltages. Okay. So this is the thing which you need to keep in your mind, that power quality is actually concerned with the supply voltages, the input voltage. And if you are experiencing in power quality, regardless of what load you have, then you must check the supply. Either it is a generator, either it is any conventional power plant, or anything else which you are getting from the grid or anything. So this is totally concerned with the quality of supply voltages. Okay. Now, as a result, PQ indices are developed mainly for the voltage waveform. As will be seen in the next section, the signature of equivalent failure in some cases can be more noticeable in the current waveform. Now, this is a very important line, that moreover, that voltage waveform has a significant role if you are checking for signatures of equipment failures. Then it is more important than the current waveform, because most of the time we do not find you can say the real faces of signatures in the current waveform, so we use the voltage waveforms. Now, the voltage signatures exhibit a very wide range of characteristics. Both current and voltage signature may be needed for the correct detection of the equivalent failure. Now, most of the time, not only voltage signature gives you the idea, but with that you have to use the current waveform for the better evolution, for the more correct or precious and accurate reading, and accurate you can say examination of such signatures. Sorry. Okay. Now, this section presents the electrical signature of various utility equipment, including the waveform and RMS plots of the voltage and currents. Now, on the second one, on the next slide from now, we will be now onwards, we will be having the different electrical signature, which I am going to explain you and tell you about the what kind of failure that has occurred, and it has given such and such electrical signatures. And these data has been collected from the real time working substations, and that have been taken from the CTs and PTs of those substations. Okay. Now, it is mentioned here the substation is probably the most feasible location for general purpose disturbance data based equipment condition monitoring, because from the substation, most of the time, the load which is connected in the load center to the grid does not generally affect the substation. So the data which you receive from the substation equipments, that is more accurate in, than the data which you take directly from the equipment terminals. Now, we have divided these signatures, this signature in the different parts that we have. As we know, there are different electrical equipments, so we have divided into different sections so that we can give you a general idea for the individual equipments. And starting from the cables, we know that cable are not only very important, but you can say as an essential part of in power system, because it gives you a path of flow of electricity from the generation to the load. And this has a very you can say not short term, but 24/7 they are working, so their signatures will gives you their signature will give you an idea that how much that cable is actually having life from the date, and how much you can say chances of their present there are present of future failure, and what you can say length of that failure, what is the duration, and how much severe that equipment failure will be. Now, most utilities process a large amount of power cables, and these cable system age failure becomes more common. Medium voltage underground cables may show sign of incipient falls before permanent failure occur. Now, what are incipient faults? This is a very important term if you are studying failure signatures of any equipment. Incipient faults are those faults which are self-clearing fault, and before an equipment getting a permanent fault or complete damage, it will gives you the sign of incipient faults. And these faults also do not have such high duration, so that the protective equipment or protective device which is installed before those equipments can get tripped. So these faults are actually, you can say, a rusting process, like in a metal phenomena, that rust before that metal gets totally broken. If you are putting in somewhere where is a high content of moisture in the air, it start to get rust, and this rusting process start to damage that metal and breaks its complete strength. And after some time, it will completely very easy to break that you can say metal of piece of that thing, just because this rusting has made the you can say molecule, the material, very weak. So these incipient faults are same as the rusting for the metals. Now, the self-carrying nature of such fault is associated with the fact that, for example, now this is for an example. So let me just give you an example that what kind of fault, sorry, I mean to say that how these fault can get self-cleared. For example, if an arc is produced just because of water that is present in that cable, and that arc produces some heat, and that heat is enough to evaporate that moisture which is already present in that cable, and that caused that arc. And due to that heating, the high pressure vapors of that moisture that has been created due to the heating of that arc extinguishes the arc. So these are the these are the general causes of self-clearing nature for such fault. Now, if we talk about the incipient failure cable, there are many kinds, like sub-cycle incipient faults, multi-cycle infinite fault, sub-cycle faults followed by multi-cycle faults. These are these will be discussing on the next slides. Now, self-clearing fault lasting about 1/4 cycle. Here you can see just a quarter of cycle has given the sign of high current, and this has cleared in the next, in just in the next part of that same cycle. Now, for the self-clearing fault lasting about 1/2 cycle. Now, in this figure, you can see that not only a quarter cycle of this waveform or voltage and current has experienced this fault, but a complete half cycle of that fault is having this, self-clearing nature. Okay, now the current waveform during a single phase incipient fault, like here is an example taken of phase C of an 13.8 underground cable. You can see here the fault has originated from an incipient failure of an XLP cable, and it has lasted the half cycle with a 2.7 kiloampere fault current. So this is a single incipient single phase fault. So single incipient means it has occurred for the single time and it has occurred on the single phase. Now we are having a multiple incipient single phase fault. This is a fault on a single phase, but it has occurred not only once but multiple times. It has occurred and it has got self-cleared. So these are the signature. Like first here in the current waveform, you can see the current has rise to an specific value. Then again it has self-cleared, and after some time, after some duration, it has again created an incipient fault, and again it has cleared. Now, multi-cycle self-clearing incipient fault. Now a fault has occurred, and that is also incipient fault, but it has not lasted for one cycle, but for one or more, you can say cycles, more than one. So that's why it's called multi-cycle self-clearing fault. Now, after several events that can occur, that can have occurred for the several hours, months, days, whatever duration of time depends upon the magnitude and the environmental condition. It will These incipient fault will cause a permanent fault. Like for example, these are the faults that had occurred at a specific time, and after some hours, it has again that caused some faults, and at the next, in the final one, you can see here the permanent fault. The cable has failed now. Now this is the permanent fault which was led by the some incipient fault that has occurred just few days or few hours or few months ago. And so these are the you can say, and at the end, due to the permanent fault, the overcurrent protection or any protection device that has operated, and now the system has shut down. Now incipient fault followed by permanent fault. This is also a same you can say kind of permanent fault, but in this permanent fault, the incipient fault has just recently occurred. So these are the three incipient fault you can see here. So these three incipient fault has that potential which caused the equipment failed just in the same you can say waveform while mirroring, and this is a more severe fault than the previous one. Now for the overhead lines, as we know, there are many cases for overhead lines failure. Such failure generally manifests as short circuit, because overhead lines are mounted on tower that work as a channel of flow of electricity, mainly from the power generation to the grid station, and then from again bigger grids, 500 to 220 grid to again 220 to 132 grids, and this goes on. No? So generally what failure occur on the overhead lines is considered as a short circuit, and this can be due to the trees branches which are and accidentally lay down on this power line and shorts the power lines that can be face to face or face to ground. So these fault can occur, but they occur for a very short time, because due to the high current, due to the short circuit, a very high amount of heat is produced, and that branch which caused the shorting of these power lines itself burned out. Itself burn out, and that again you can say goes back, and that fault has cleared now. Okay. Now the voltage and current waveform during a tree contact are shown in the 2.1. Now I'll be going to show it to you. Now as you can see here, this current waveform gives you the short circuit value for that tree contact that has just lasted for a single cycle. And during this current, during this short circuit, the voltage has dropped to 20% or more than 20% of its rated voltage. Okay, now let me just give you another example. Here is an arcing fault caused by tree contact seen downstream. Now this current over here shows you that a short circuit has occurred, but it is not only short circuit, it has caused arcing, because not in a single cycle but for the multiple cycle it has caused this current. And during this current increase, during this arcing, the voltage has shows a drastically change, and it has went from the it has went to a very low value. Now this behavior gives you an idea that this is just because of an arc that may have caused by tree contact, any bird contact, or any other conductor that has accidentally you can say laid on these overhead lines, and it has caused the arcing due to a very long duration of shorting. Now, this theory I'm not including because of you can say these are whatever I have given you in verbally, that is already present in the text. So I'm giving you a general idea, and you can say a summarical view of these waveforms. Now, the first episode series of three contact events. Now, as you can see here, a tree contact has occurred and the voltage has went down due to the high currents over here. Now this is the RMS values of current and voltage. Now these are the second episode of series of tree contacts. Now again, for the second time, the tree has made a contact with these power lines, and it has occurred the same you can say behavior of current and voltage we can see in these waveforms. Now this is the third one, and these are the you can say just these were the you can say given just because to give you an idea. Now the current waveform during a single phase fault on the phase C of a 25 kilowatt system is shown in 2.7. Now this tree contact caused the primary to burn down. Okay, now this is the phase C, and although this event is about a permanent failure, the signature can be considered as an extended version of an incipient fault signature. Here you can see that the two phases were not giving you a strange or any unwanted waveform, but only the phase C has shown as a here as a some you can say unwanted, undesirable behavior. Now the failure signature of transformers. As we know that there are different parts of a transformer, so we cannot give you a general signature for each of for all the equipments, but it is good or it is feasible for us to give you a separate you can say signatures of those component failure. We have taken only two components over here, that is the tape changer of transformer and the bushings, and the other equipment or components will be discussed in the if we get chance to deliver the same webinar with an extended you can say version, so we'll be including those parts in that webinar. Now, failure of tape changes. uh, in the figure 3.1, uh, illustrate a case of load tape changer failure. Initially, the monitor reported zero current value on the one phase for less than one cycle. This anomaly happened several times each day. Over a following several days, the duration of such anomaly increased to just over one cycle. Now, the utility scheduled a maintenance to investigate the root cause of such nature. The technician found a pin which was shivering, sharing, and resulting in arcing when the load tape changer moved. After a planned maintenance, it was believed that a catastrophic transformer failure would have occurred within 2 weeks if the arcing have not been detected. So this is a very severe issue, because this just waveform which is giving an unwanted behavior of voltage for just a one cycle, it has provided you a warning that if this maintenance was not being scheduled, you wouldn't be able to find the root cause of this incipient fault, and that would have lead to a permanent failure of the transformer, just because of a very small part that was pin that was shearing and had a loose connection that has caused an arcing, and this would have caused a very catastrophic destroying effect to a transformer. So this gives you an idea that what is the importance of these failure signatures. Now, failure of transformer bushings. Figure 3.2 shows a voltage and current waveform during an arcing fault on 12.47 feeder, which is due to the bushing failure on the distribution transformer primary winding. A recloser cleared the fault in about two cycles. The measurement location in this case is along the feeder, not at the substation. Now, here you can see that the voltage on this part, on this area, has shown as a very unwanted behavior. The voltage has dropped, and some few cycles here, a very short transients are present over here, and the current also gives you a very you can say sub transient current value over here. Now this, as we have already discussed in the previous slides, that this signature shows the arcing fault. Okay, so and this has caused is the bushing failure. Due to the bushes, it was shown in the feeder reading. Now, switches in this section refer to any circuit breaker, switches, closers, or whatever. And this switches does not only cover these circuit breaker or you can say closers, but it has in every type of switching that is included in the power system. Now, power system switches are having that capacity of tolerating very high wear and tear over time, but they are manufactured on such basis that they can handle such stress in mechanically, electrically, and whatever. This section presents the failure signature of different types of switches in the distribution system, like line switch, An overcurrent fault occurred, leading substation breaker to trip and reclose twice. The fault was cleared without a need of permanent service outage. This sequence of event was in accordance with the usual fault and protection sequence, except for the behavior of phase A current after a fault clearance. Such current presented as an irregular behavior different from the other phases and from the fluctuation caused by regular load variation after a fault and trip event. This fault and post-fault currents are shown in 4.1. Now, this current is giving you an idea that how how many times of these you can say switches have been closed and what and how many times the fault has occurred. Now, this is the primary RMS amperes for a date for and just you can say at the 3 second or 46 minutes, and after 40 seconds it has again caused another fault. Okay, so this has given you a sign of temporary fault, na? So these are the signature for both. Now, arcing of capacitor bank switch. Now, the current waveform and arcing capacitor bank switch during energization of 300 kVAR capacitor bank is presented in the figure 4.2. Repetitive transient can be observed in the figure. Now, these phenomena of transient at the closing is called multiple pre-strike. When closing a switch, a pre-strike could occur if the electric field strength exceeds the dielectric strength of the contact gap. Okay, inrush current with high frequency and high amplitude flows through the switch. And this multiple pre-strike is clear at the nearest zero crossing. Here is a signature for those like it has switched and it has called the arcing fault over here. And again at the negative cross after the arc extinguished, it has again you can say caused multiple pre-strikes over here, and then after complete closure it has went to a smooth current waveform. Now, failure of light and surge arresters. As we know, the surge arrestor and lightning arresters play a very important role for the surge diversion and the protection of and substation at the first hand, because whenever the two substation are connected, the substation starts from the surge and lighting arresters isolators, because the high amount voltage can cause the substation equipment to out or can cause a very high impact, and for that we install lighting and surge arresters to protect these equipments. Here you can see that there is a burst of intermittent arc fault, and these are the RMS multiple arc burst, and this is the final failure of such equipments if there is a failure and already present. Now, this is the signature for the surge arrestor fault. The previous one was for the lightning arrestor, and this is for the surge arrestor. Lightning arrestor and surge arrestor both have the same phenomena of working and same construction and structural view, but they have a little bit difference in their functions. The purpose of use, lightning arresters are used for the lightning purpose, that if there is an lightning happened caused the high voltage change in the power lines, so this lightning arrestor diverts that surges or that high voltages, and surge arrestor are used for those high voltage caused by the switching or any equipment failure which has caused the high increase in the voltage, and that is diverted by the surge arrestor. So this was all. Das ist alles. Anything you would like to add? Any question you would like to add? You can tell me, and you can ask me any suggestion, or you can mail us. Yeah, you can also mail us if you have query for the next time. Yeah. So you will find this presentation on YouTube, on our YouTube channel, that is Tahir Saleem UES. Okay, you can search it out and you will find over there any question you would like to ask or not. You can mail us your queries on the email, Any suggestions are is also welcome. Okay, thank you very much for attending this webinar. Allah Hafiz.